Next, we'll take a look at a couple of analysis tasks related to a sample. So the idea is that for pump shaft L2, we need to take a random sample, a size 10, tabulate measurements for one section, and then ask the question, if more measurements are taken, what's the expected range for 95% of the measurements? We'll use and assume a t distribution, look up a student's t, and then define a precision interval range based on one student's t value away from the standard deviation. The second question, very related but slightly different, is to compute the 95% confidence interval for pump shaft length L2 using that same sample. The difference with the confidence interval is that we'll use the standard deviation of the means or the standard error instead of standard deviation in computing the range. So if we look back at the measurement that we're taking, the shaft measurement L2 is an interesting and challenging measurement to take. It actually requires using a step face measurement with the vernier caliper, and we expect it to be 52. So with that, we will go ahead and look at our data. And we can see we have our data for all of our measurements here. So this is in our Google Sheet, and we're going to filter down on just the L2 measurement for one section. So we'll clear these, and then we're looking for pump shaft L2. And we're going to choose just one section, and we'll start with actually section 10. Okay. So with this, we can compute some statistics. We've already got our conversion to metric in here. So if we go ahead and just look at our data like this, we can insert our pivot table and make a new sheet for that. And then just grab values of measurement value, and we'll get the average and standard deviation. So the average and standard deviation. Okay. So the average and standard deviation of L1, let's go ahead and add the measurement component in here. Where we filter only on L1. And we filter only on section 10. Shown here. So we don't need to display the totals. We can take that off, but we certainly can see that our measurement average is 51.49 and standard deviation of 2.06. So not too bad of a standard deviation, but this is the standard deviation of the population. And so this isn't what we're going for. We want to have a sample, and we want the sample to be randomly taken. So how do we do that? So how do we make a random sample? Well, one way is to make a random number. And so we can use several functions, but we'll just start with a rand. And with rand, we get a number between 0 and 1. Okay. And if we click down there, we get a bunch of random numbers. Now, we want to actually copy these, Control-C, Alt-E-S-V, and paste them so we're not using the function anymore, so that the random number doesn't update every time we do an operation. With this now, we can take our data and we can sort it and we'll use a data row here. And now we're going to sort by random number. It doesn't really matter if we go A to Z or Z to A, ascending or descending, as long as we choose one method and then we sort our data. So with that, we have pump L2 measurements, and here we actually had a total of 29 measurements. So we're taking a random sample. So to get our random sample, we just count down and then just say 1 and or the row number plus 1, and we go all the way down here. Oops. Actually, that isn't adding the row in correctly because our filter is applied here. So we can just use our count function to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over here on the side, you can actually just show count, and then you can see with that we have a count of 10, and then now we can just, for the sake of visualization, we can highlight it. And this is now our sample. So we'll just call this sample, and we can call it yes for these guys. And these other guys are not our sample. We'll later use this as a filtering criteria when we compute our statistics. So now we need to really just go back and compute our mean and standard deviation of our sample. And so let's go ahead and do that. And so again, we'll take all the data here. And actually, I think maybe the simplest way is to go ahead and just copy this and make a new sheet and then paste values. Okay, so we'll hide that column. And now here we have our random sample and our values from that random sample. So with this, we'll select the whole thing, and then we'll do insert pivot table. We'll just create a new sheet, and we'll also do, we'll have the rows be the measurement component. There's really only one measurement component. And then we'll have the values be measurement value, and we need the average. And then we need to add a measurement value standard deviation. This time, instead of the standard deviation of the population, we're going to take the standard deviation of the sample, which uses n-1 in the denominator for that. And so that's our measurement here, just to be thorough. We can add a filter for the yes, no, and we'll take only the yes samples. And we can see that with our sample, we have a sample mean of 52.116 and sample standard deviation of 0.182 millimeters. So we're being asked for our 95% precision interval range and confidence interval range. So with this, our 95% precision interval range, so the range of values we'd expect if we take more samples with 95% confidence. That's going to be our X bar, so our mean, plus or minus students T as a function of N, the number of samples, and P, the probability. We'll put that sort of in that kind of notation like that, times the standard deviation. So standard deviation, and we'll just put sample. Okay, so we just write S of X like that. Okay, so we need to find our students T, and so there's different ways to do this. And so let's go ahead and just make a note here of students T for 10 at 95%, and then we'll look it up. So one thing to do is to use a reference table for students T. Just as a visualization for what students T is doing is for a finite set of data, students T is giving us a correction factor for smaller samples. And visually, if we look at the normal distribution, we can see that this is what it looks like, this sort of bell-shaped curve here. But the more samples we have, the more the sample distribution takes this darker curve. The fewer samples, we have a lowering of the probability in the middle and a widening of the tails, or higher probability in the tails. So here we see our 95% range, which gives us 0.025% in each of the left and right tails. And we use a student's T. So the student's T is tabulated as a two-tailed distribution, and nu is what's called the degrees of freedom. It is n-1. So our nu degree of freedom is 9. And the probability that we're interested in is 95% probability. So our student's T from this table is 2.262. So this is 2.262. And so that's at a P percent of 95, an N of 10, and the nu, or degrees of freedom, of n-1 of 9. Okay, so we can actually also use Google Sheets to compute that student's T as well. And so we can use this function in here that's called t.inv.totail, 2t, to get our student's T for a 95% probability. And so that's tabulated in this table here. Like table 4.4 that was just referenced, this goes down to degrees of freedom of 60. And then after that, effectively is an infinite number of samples, where the coverage factor is effectively like a z-score, where this particular table fills in the blanks and does go up to, it looks like, much higher in terms of the samples, 200 possible sample size. So then our precision interval is the mean. So 52.116 plus or minus student's T 2.262 times our standard deviation, which is 0.182. Okay. And so if we go ahead and calculate that, we have an upper, we'll call it upper 95% range, and a lower 95% range. And so we have equals the mean plus T times standard deviation. Should be C2. So we have an upper range of 52.59, and our lower range is the mean minus student's T times the standard deviation. So our 95% precision interval range, which tells us if we take more data with 95% probability, we expect the measurements of L2 to be within 51.703 to 52.529, which makes sense because the nominal measurement is 52, and so that's the 95% range. Now, the 95% confidence interval is very similar to that. So 95% confidence interval except that instead of using the standard deviation, we use the standard deviation of the means, which is also known as the standard error. And for the standard error, so we usually call it subscript S sub X bar, that's equal to the standard deviation of the values of the sample divided by square root of n, the number of samples. So it's pretty simple. So S sub X bar is the standard deviation equals the standard deviation divided by square root of n, the number of samples, 10. Okay. And so 0.0558 or 0.0577. So then the confidence interval range, so what usually designated by CI, so 95% CI or confidence interval, that is equal to the mean 52.116 plus or minus students T, and we'll just students T for given degrees of freedom for given probability times the standard error S sub X bar. Okay, so our CI upper and our CI lower is equal to the mean plus students T times standard error, and then the lower is the mean minus students T times the standard error, and that's L2 in millimeters. So the range for 95% confidence interval is 51.985 to 52.946 with a sample randomly selected of 10 measurements from our population. So that answers the first two questions related to 95% precision intervals and confidence intervals for this data.